Today on How It's Made. Scuba diving lights. Interchangeable sandals. Race car simulators. And fiberglass doors. A dive light is essential when scuba diving at night, but can also be used for daytime dives to explore underwater caves and shipwrecks. The deeper you dive, the more water absorbs certain colors in the light spectrum. When you use an artificial light, you can see the underwater world in true color. The dive light is waterproof to a depth of 295 feet. It's brighter than a car headlight, with 6 outer LED lights for floodlighting and 3 inner LEDs for alternate spotlighting. The dive light begins as a conceptual drawing. The mechanical designer sketches out its basic features and a few proposed shapes. Then the company creates foam models. Scuba divers test these models and provide feedback on the comfort of each shape. This market research results in the final design: a compact hand-mounted dive light with a user-friendly operating switch and 3 LED battery life indicators. The housing's components are made of durable plastic pellets, reinforced with glass fiber. Workers load the pellets into an injection molding machine. The machine melts them and shoots the molten plastic into the proper mold for the component they are making. The machine then cools the plastic to a solid state and ejects the newly formed part. This is the reflector. It combines the light from the 6 outer LEDs into a single beam. It's coated in aluminum to increase the amount of light it reflects. A 3D printer produces prototypes for all of the parts before they are manufactured. Guided by a computer, the printer shoots out plastic to build the part in 3 dimensions from the bottom up. Once the prototype is approved, they make a mold for mass production. This part is called the light pipe. It has oval covers for the 3 LED battery life indicators and a waterproof seal. Once all the housing parts are molded, assembly can begin. They insert the light pipe into the main body of the housing. Then they attach a switch, which turns the light on and off. It also toggles the light between spotlight and floodlight modes. They don't need to pierce the housing to connect the switch. The switch slides a magnet over the outside of the housing. The magnetic field communicates through the housing to sensors inside. Next, they insert and connect the circuit board. Then the lithium-ion rechargeable battery. They plug its connector into the circuit board. This cover holds the internal parts in correct alignment. A silicone O-ring forms a watertight seal between the main body and the light head. They snap the reflector over the 9 LEDs, which are attached to a round circuit board. The circuit board is metal so that it will absorb the heat the LED lights generate. The screw-on aluminum bezel makes contact with the circuit board, transferring the heat out of the housing and into the water. They conduct the first quality control test in water. The dive light is turned on to verify that it will run for 65 minutes on a full charge. In the second quality control test, they submerge the dive light in a pressurized tank. This simulates the pressure the light would be subjected to at an underwater depth of about 300 feet. That's over twice the diving depth of a typical recreational dive. If the light doesn't spring a leak, it passes the test. They fully recharge the battery, which takes 2.5 hours. At full charge, all 3 indicators light up green. As the charge drains, the indicators change from green to orange to red, then to flashing red. So scuba divers are never in the dark about how much juice is left in their light. Interchangeable sandals come with numerous ties that can be used to customize the look of a pair of heels. The mix and match possibilities are endless. The wearer can try out many different styles on a small budget. With interchangeable footwear, you can change the look without actually changing your shoes. With a variety of cloth and leather strappings to choose from, a pair of sandals can be made to look different each time you wear them. To make a pair of interchangeable sandals, they start with a piece of hardwood like cherry, walnut, or maple. The employee cuts the wood to a workable size. Then, computer-driven routers carve the rough shape of the sandal's heels, making 2 heels from a single block. The router sculpts a cup for the wearer's heel and carves a supportive structure for the arch of the foot. The router then shaves the sides of the heels and exposes the grain of the wood. Then a worker takes over, cutting away excess wood with a bandsaw. She rounds the back of the heels and further refines the structure. She now has a pair of heels. Another team member brushes rubber cement onto the soles. They are made of both natural and synthetic rubber. She applies glue to the heels too. She presses the heels to the rubber soles. The glue takes 40 minutes to dry. Faux leather backed by cushy padding is used to make the footbed. This material is similar to what is used to make flip-flops. The worker transfers the footbeds to a silkscreen workstation. She lowers a stencil with the company's logo on it. She applies acrylic ink and squeegees the ink across the stencil to transfer the image to the faux leather footbeds. Another employee threads strong nylon cording through the holes in the footbeds to create loops for the interchangeable ties. He presses rivets into the footbed to hold the loops in place. Then he attaches the second part of the rivets to the protruding shafts. Using a special press, he flattens the rivets to secure them to the footbed. The loops are now firmly attached and should hold up to frequent tying. Another worker now glues the footbeds to the soles and heels. Next, she glues the rubber heel caps to the bottoms of the shoes. The caps provide tread and make the shoe more durable. A worker then sands the sides of the sandals, blending all the layers together. He buffs the sides against a fine grit abrasive to give the surface a nice sheen. Then he rubs an oil-based sealer into the wooden heels. This protects the wood from moisture and also accentuates the grain. It's time to test the ties. She threads the ribbons through the loops. They're good to go. With many colorful ties to choose from, these interchangeable sandals are many shoes in one. Race car simulators help train race car drivers off the track. They provide realistic visuals and sensations, bumps, jolts, swerves. Whatever movement you'd feel if you were sitting in the driver's seat of a real race car. This race car simulator can be programmed to produce a range of racing scenarios and weather conditions. It can replicate any car on any track. First, a computer-guided laser cuts many of the simulator's parts from steel sheets. After workers sand the rough areas, a machine reads the final shape with a laser to make sure the part meets specifications. If a part requires bending, it is done with a press. This is one of the side brackets for the driver's seat. The simulator's main structure is made primarily of steel tubing. They saw the lengths required. Then a computer-guided mill drills holes for the bolts that will later be used to attach the simulator's components. Once all the steel tubes are ready, a welder puts them in a jig to align them correctly for assembly. The structure's tubular parts are welded together. Then the worker adds the simulator's sheet steel parts and sprays the structure with industrial-grade paint. Now they mount an audio speaker and amplifier for the vibration system. Motion controllers that move the steering wheel and driver's seat are also added. They install the power distribution block and a subcontroller for each of the two actuators. They install the cables required for the simulator's components and plug them into a USB hub. Then they install the computer and plug it into the USB hub as well. They cover the top of the structure with a textured aluminum panel. They bolt the bottom of the actuators to the structure and plug them into the subcontrollers inside. Then they mount the driver's seat and bolt the top of the actuators to the back of it. A worker installs the seat belt along with the spring mechanism that yanks the belt back when you hit the brakes. They close in the sides of the main structure with aluminum panels. Next, they assemble the simulator's 3 pedals, gas, brakes, and clutch, and mount the clutch mechanism to it. The pedal assembly is installed to the base of the steering frame. They mount the dashboard to the top of the frame. It's made of carbon fiber and contains the computer and audio controls. They attach the steering frame to the main structure. Then they assemble the steering wheel. Inside its base is a circuit board that controls the buttons on the wheel and gear shift. It's called the shift paddle. They mount the shift paddle to the base, then flip it over to attach the wheel. Next, workers assemble the display frame. It holds the simulator's 3 monitors and 3 front speakers. Then they roll in the rest of the simulator and plug the monitors and speakers into the computer. Finally, the steering wheel is mounted to the dash. It snaps in and out, allowing the driver to easily switch between steering wheel models. The simulator is run through several days of test drives before it ships out. Amusement parks also purchase these simulators to offer visitors a race car driving experience. They can even link multiple simulators together to race against each other in virtual replicas of the world's most famous racetracks. In the 1980s, fiberglass doors came on the market. They were well insulated and didn't warp in humid conditions like wood doors. However, they lacked the beauty and texture of real wood. That's now changing with technology that can make fiberglass doors look much more inviting. Fiberglass doors trick the eye and fool visitors. Even up close, they look like real wood. It's an illusion made possible with the help of technology. A wood-grain fiberglass door starts with a real wood door. A computerized cutter carves various panels. An employee sands away any marks left by the cutter. He gently scrapes the wood with the wire brush to expose the grain. He then assembles the panels of the door within a special fixture. Another team member scans the wood door with a laser to confirm its dimensional accuracy. With that confirmation, they're ready to use this wood door to make a fiberglass one. Next, the worker pours a special silicone mixture onto the wood and leaves it to cure overnight. This step was demonstrated using a smaller section of the door. The silicone picks up all the definition of the wood grain, creating an exact copy of the door. Next, an employee injects a different silicone mixture into a thin gap between the recently created silicone copy and a sheet of steel. The second silicone door copy is thinner, allowing for a better transfer of heat during the next process. They load the door copy, still on the steel sheet, into a chemical deposition chamber. The chemical heats the steel and the silicone, causing a nickel vapor shell to form. The nickel shell has all the detail of the original wood door. An employee files the edges and adds a protective fiberglass cover over the top of the shell. Workers then lower the nickel shell into a mold base. They remove the protective cover and are ready to use the nickel shell to mold fiberglass door veneers. There are many nickel molds and a variety of door styles at this factory. The fiberglass material now unwinds into a cutting station. A worker slices it into uniform strips. The fiberglass has a dough-like consistency at this stage. He places a stack of fiberglass strips on the nickel door mold and lowers a hot press. The press squeezes and melts the fiberglass. It flows into the crevices of the mold. The fiberglass solidifies quickly. An employee removes it from the press and sands the ragged edges. Another member of the team confirms that the width and thickness of the panel are on target. They stain every first-run fiberglass panel to expose the transferred wood grain. This is a test. If the grain is good, it means there are no defects in the nickel door mold. It's time to assemble the fiberglass door. Rollers apply glue to external framing wood. The team builds a frame around the fiberglass door skin. They join the wood to plastic casing at the top and bottom of the door. They place a second fiberglass door skin on the top. Then they feed the door through rollers that squeeze it together. This activates the glue for a strong assembly. The glue takes over 24 hours to dry. Next, they load the hollow fiberglass doors into an insulating press. The press closes, holding the doors tightly in place. A worker fills the hollow doors with polyurethane insulating foam. When foam begins to overflow through the vent holes, the worker knows the doors are full. He caps the fill hole and runs a finger along the doors to remove any excess foam. Energy efficient and stable, fiberglass doors are a great alternative to wood. With eye-catching wood grain, they're convincing imitations. If you have any comments about the show, or if you'd like to suggest topics for future shows, drop us a line at sciencechannel.com/howitsmade.